Okay, hello everyone. I welcomes to all in our lecture series on optics. Belongs to B.sc Physics Hons syllabus. Second semester. This is your core 4 paper. Okay, we are discussing Fresnel's diffraction. This is your part 3 video on this topic. In our part 1 video, we discussed introduction about diffraction, Fresnel's assumption, Fresnel's half period zone. Part 2 video, we discussed corner spiral or Euler spiral in detail. Okay, in this video, part 3 video, we are going to discuss this one. So here I am going to suggest to all of you that before you are going to start this part 3 video, you just watch part 1 and part 2. Otherwise it will be somewhat difficult for you to understand this part 3 video. Okay, so let's start today's video or class. Okay, so in our last class or last video, we discussed in detail about Coronal spiral or the so-called Euler spiral in our second part video. So how this spiral will be formed in detail we have been discussed in our last video. Here you can see S and S dash are two extremists of the wavefront. Uh, how see see here from O to M1, these vectors are is belongs to strips of the first half period zone. Of the first half period zone, whatever we consider, for that these are the vectors. These red vectors. So these vectors from M1 to M2, the vectors are belongs to second half period zones and its corresponding strips. Okay. So if I am going to consider entire wavefront, this one, whenever it will be passed through this slit, here you can see this is your plane wavefront, and when it will be passed through this slit M and N, that means this entire plane wavefront is going to considered as half period zones as Fresnels. So according to Fresnel, this plane wavefront is going to be considered or assumed as the Fresnel half period zones. And here each and every zones further subdivided into strips. This is like this for the first half period zone, for the second half period zone subdivided into strips, and we are going to get this corner spiral in first quadrant as well as your second quadrant. So here S and S dash are the two extremists of wavefront. Okay, which is passed through the slit. Here you can write, it will better. It will be better that here you have to write it. Okay, so I am going to write it here that which is passed through the slit. Okay, passed through the slit, right? So here M1, M2 are represents the age of the first and second and so on half period zones of the upper portion of the wavefront. Likewise, here you can see here you can see that M1 dash, M3 dash, M1 dash here, M2 dash, M3 dash, M4 dash, M5 dash are the lower portion of the wavefront. So here you can say if this is your M1, then this will be considered as M1 dash. This is your M2. M2 will be here, right? M2 will be here means this will be called as M2 dash, like this. So M1, M2 are represents the age of the first, second, and etc. half period zones of upper part of the wavefront. Likewise, you can write over here that M1 dash, M3 dash, M5 dash, M2 dash, and so on for the lower portion of wavefront. Okay. Now, In this video, we are going to discuss about uh, your Fresnel's integral. For Fresnel's integral, this relation is important to know. Here you can see the characteristics of this curve is that for any point P on the curve. So this is our spiral curve. Suppose this is any point P on this curve. The phase angle is directly proportional to the square of the distance. So this is the phase angle. Suppose if I am going to consider P over here, then the phase angle will be this one. If I will consider this with the P point, then here I am going to draw the tangent. This will be the phase angle. Okay. So here this phase angle is the directly proportional to the distance viewed. Here distance means, suppose we are going to consider the P point is here and we are going to draw a tangent over here. This is the delta phase angle, and here V is considered as small v. Small v is considered as the distance from O to that point P, like this, like this. So this distance from this point to this point, this distance is nothing but called as your V. So here characteristics of this spiral or Coronos spiral, or we can say Euler spiral, is nothing but phase angle delta is proportional to the square of the distance. This distance measured along the length of the curve from O to P. So if we can determine, or if we can prove this one, phase angle directly proportional to the square, then this will be help to find out the Fresnel's integral. Okay, Fresnel's integral, whatever we are going to discuss in this video part 3. Okay, now we are going to find out this delta is proportional to small v square. Okay, okay. Here this one, here I have been highlighted these two lines. Okay, now we are going to go for to prove that delta here, how the phase angles, here you can, how this, okay, how this phase angle delta is proportional to square of the distance v, that we are going to prove first. Then automatically Fresnel's integral will be found at the end of the discussion. Okay, so here you can see a wavefront is traveling along this direction from this source S, right? So here we can see that from S the light can be traveled along this direction, S to O. This is your O and this point is your M, this point is your N. S to O to P and S to A to P. So already we have been discussed in our first video already discussed how to construct the Fresnel's half period zone. So if this is your wavefront, on this screen we are going to consider a arbitrary point. From the arbitrary point we have to consider the various radius. Considering the radius, we have to draw the imaginary spheres in 3D or circles in 2D, and it will be cuts the wavefront, and we are going to the half period zones. So for this circle here we are going to get a half period zone. If we are going to consider another imaginary circle, then it will cut the wavefront, and here we are going to get another half period zone, like that. Already we have been discussed how to draw the half period zones or construct the half period zone in our first video. You go through that video number 1, Fresnel's half period zone, video number 1, you go through that. So here you can see, if this is a source and light is allowed to travel along this direction and it falls on the screen, then through this half period zone it will be fall on the P, and through this half period zone it will be fall also on the P. For this half period zone it will be go from S to A and A to P through this path, S to A and A to P, right? For this half pillar zone, it will move from S to O, then O to P. Now we have to find out what will be the path difference between SAP and SOP. Here, easily it can be observed that this path SAP is larger than SOP. But we have to find out. Okay, here path difference between the two waves between the two waves traveling in the directions SAP and SOP is given by, here you can see, for SAP this is your SA plus AP, S to A, then A to P, right? Then another path is your S to O to P, right? So here SOP is nothing but S to O and O to P. Okay, and this is your M point. If I am going to draw a perpendicular, then this is your A point, sorry, M point, and from this point B, if I draw the perpendicular, this point is your N, and this connection, first half pillar zone connection, is your O point. This is your O point, right? Now SA, here you can see AS to A is approximately A, because if this angle will be decreased, then this A point will be come down, and suppose A point come down over here, so this length will be approximately with A value. A is the distance from S to O. Okay, from S to O is your A distance. Okay, if I am going to consider for small angle, then AS to A distance will be approximately A. Okay, that I substituted over here. Then AP, carefully observe, AP, A to P, A to P value, A to P, sorry, A to P distance is nothing but A to B, then B to P. Likewise, if I am going to consider this is a small angle, then here you can see BP, this BP will be approximately B. If B will be come down, for the small angle B will be come down over here, then here you can see B distance, that means O to P will be approximately B value. Okay, then AB is there, AB I written. Okay, AB plus B to P will be approximately small b, minus SO from here to here, SO is your A and O to P is your B. I just substituted over here, right? Now here you can see A plus B minus A plus B. So both are got cancelled, and we found AB is the path difference between these two waves traveling along two different paths, SAP and SOP. Path difference we found AB. For now, here another thing also can be observed. Here you can see for large distance of A and B, AM and BN can be taken to be approximately equal, and path difference will be this one. Okay, carefully you have to watch. For large distance of A and B, large distance of A and B means, suppose if I am going to consider source will be at larger distance, suppose this source is a larger distance here S, and suppose the screen at the larger distance at here, this is the screen at point P on the screen, suppose here we are going to consider. So here you can see, if I am going to join this point A and then this point over here, then we can found that AM this height and this height will be approximately equal. So as much as we are going to go away from this point O, that means if I am going to consider A is so large and B is so large, then this height AM and BN will be equal. See, if I am going to consider again a larger distance towards this side, then it will seems to be A and B at equal height. A and B will be at equal height. If it is so, then this distance will be equal to this distance. So if A and B will be equal height, that means AM and BN will be approximately equal whenever A will be larger and B will be larger, then AB distance will be approximately equal to MN distance, right? So same thing it has been written for larger distance of A and B, AM and BN can be taken to be equal approximately uh, e- uh, can be can be taken to be approximately equal, or you can write taken to be equal approximately, whatever you can write. Okay, and path reference D. Now path reference we found AB here. So if AB equal to MN, so here D will be equal to AB approximately equal to MN, right? And MN is nothing but MO plus ON. So here M is the this point, N is the this point. So here M to N distance is nothing but M to O, M to O, then O to N. Same thing it has been written. Okay. Now, but from the circle, property of the circle, MO. Here you can see MO, M to O. This distance MO is nothing but AM square by 2 SO by 2 into SO. See, if I am going to consider this is the, see, this XY is the portion of a circular wavefront, right? So if I am going to consider the full circle, according to the property of the circle, we know that this distance, MO distance is nothing but AM square, this is the perpendicular, AM square by 2 into SO, by 2 into SO. Here SO is the so-called radius, okay, for this, circle, okay. So according to the property of the circle, it will be AM square, this distance square, by 2 SO. Here AM is considered as H height, so that, so instead of AM we can write H, so H square by 2 SO. SO we know that how much, from S to O is your distance A, so 2A distance, okay, 2 into SO, 2 into A, right? Similarly ON, if I am going to consider this circle, ON, this distance ON will be equal to BN square, this perpendicular, BN square by 2OP. 2OP means 2 into this radius. 2 into this radius OP. Okay, this radius value we taken as B, and BN is approximately AM. Already we consider over here for the larger distance. Okay, so here instead of BN, what we can write, H. So H square by 2 into OP. OP is nothing but 2B. So H square by 2B. Right. Now D. D we found equal to how much? OM plus ON. So instead of OM, MO plus ON. Instead of MO, we can write how much? H square by 2A. H square by 2A. ON. For ON also we can write H square by 2B. So here we can write H square into A plus B. If I am going to add these two terms, then H square into A plus B by 2AB. Right? Okay. If AM, next, if AM will be the radius of the nth half period zone, here you can see AM. Here this is the AM. See, whenever I am going to consider the imaginary circles like this, imaginary spheres or imaginary circle. For 2D case imaginary circle, for 3D case imaginary sphere. Actually this is the imaginary sphere. For imaginary, whenever we are going to consider imaginary sphere, it cuts the wavefront, it will create a Happier zone. Again, it another circle or sphere cuts the wavefront, creates the another Happier zone like this. Happier zone. Okay, Happier zone. Suppose here at this point cuts a this type of sphere, this type of imaginary sphere. Suppose cuts at a, it will create a Happier zone like this. Okay, let consider for this point a nth half period zone is formed. Okay, so if am this am distance is the radius. See, if this imaginary sphere is going to be caught at a, we are going to get a half period zone like this. Okay, and corresponding radius will be, obviously this will be the am. This am will be the radius of this half period zone, circular half period zone. Let am is the nth, radius of nth half period zone. So if am will be the radius of the nth half period zone, then this path is equal to n minus 1 lambda by 2. Already we have been discussed that for this path and for this path reference is lambda by 2. For from first half period zone to second half period zone, if I am going to consider for to the second half period zone, this is lambda by 2. For third half period zone, if I am going to consider for the third half period zone to first, it is 2 lambda by 2. Then for fourth to first, 3 lambda by 2. Likewise for nth, it will be n minus 1 lambda by 2. If I am going to consider nth half period zone to the first half period zone, then b plus n minus 1 lambda by 2. These things already we have been discussed in our first video. Okay, so the condition will be, here you can see, if it is so, then the path difference will be equal to n minus 1 lambda by 2. Obviously n minus 1 lambda by 2, right? That means here we found, here this path difference is represents what? This path difference is represents the path difference between this path and this path. Here I consider A is belongs to nth half period zone, and this is belongs to, this path is belongs to a first half period zone, and this A point is belongs to nth half period zone. For if I am going to consider nth half period zone and first half period zone, then what will the path reference? Path reference will be n minus 1 lambda by 2. Already here we discussed. Okay, n minus 1 lambda by 2, right? If I am going to consider first half period zone, for the first half period zone this distance is b, and for nth half period zone, what will the path reference? N minus 1 lambda by 2. Okay, so same thing we written over here, n minus 1 lambda by 2. So hence path reference whatever we found will be equal to this much. Path reference is your how much? H square into a plus b by 2ab equal to n minus 1 lambda by 2, right? Okay, now we know that lambda, the lambda path difference, for we know that for the lambda path difference, phase difference is 2 pi, that we know. Hence for d path difference, the phase difference will be 2 pi by lambda into path difference. So here the path difference will be, 2 pi by lambda, and we are going to substitute this d value. D value is how much? This value I am going to substitute over there. Okay, if I will substitute over there, then it will be h square into a plus b by 2ab, right? So here you can see pi by 2 taken outside, pi by 2 taken outside, so 2 h square a plus b is there, 2 h square a plus b, and a b into lambda. Okay, so here we found pi by 2 into 2h square into a plus b by a b into lambda. So mathematically, if we are going to calculate this value. This value will be nothing but square of the distance from here to here. Okay, mathematically, if we are going to calculate, this value will be nothing but here from this point to this point, this distance square. Here I not calculated it in detail, but mathematically this value is nothing but square of the distance from here to here. Okay, so here I written pi by 2 into v square. So here we found phase angle delta is direct proportional to the square of the distance v, where v is the distance measured along the length of the curve from O to P. From O to P. Okay. So here we prove that this delta is proportional to this distance from O to any particular point on this corner spiral. Okay. Now we are going to go for the Fresnel's integral. Okay. For any point, whatever we discussed, that we are going to follow over here. For any point, here you can see, for any point, the coronal spiral, for any point, here you can write, for any point on this coronal spiral, okay, for any point on the coronals, any point, for any point on the coronal spiral, the x and y coordinate are given by two integrals known as Fresnel's integral. Okay, how it is? See, consider a point P on the spiral. Suppose this is our so-called coronal spiral. This is the point P. Whatever we consider this is the point P on the spiral. The distance of the point along the curve from the origin to P, from this origin to this point, this distance we consider as small v. The tangent to the curve at point P makes an angle delta with x-axis, obviously. So if I am going to draw a tangent, this is the tangent through this point, this is the angle delta makes with the horizontal x-axis. Okay, for a small displacement dv, if I am going to consider, this is the small displacement from O to, this is the small displacement. Suppose this is our small displacement. Suppose this is our small displacement, and d small dv of the point P along the curve for a small displacement of the point. Suppose the point P, it is displaced from here to here, a small displacement is your delta V. Let the corresponding changes in the coordinates in the coordinates of the point will be dx dy. See here, what is the change at point O? Dx equal to 0, dy equal to 0. Now this point suppose moves a small distance on this curve from here to here, suppose. So it changes. See, this spiral is like this. Its x and y axis continuously changes, right? So from, suppose we are going to consider this is the point. This is the point. So here you can see from O to this point, it's both x and y axis value is going to be changed. So for dv distance, the x coordinate value and y coordinate value, suppose dx and dy, right? Then if it is so, if it is dvc, here suppose this is the point, and suppose the small point, if I am going to draw a perpendicular and this is the angle delta, then this is the distance. Suppose this is the distance delta v, and this is the delta angle. So obviously this will be how much? The horizontal component will be dv cos delta, and the so called vertical component will be dv sin delta, already written. Okay, so for this triangle, if I am going to consider for this triangle, and this is the delta, then and this is the small displacement, then this horizontal component will be dx equal to dv cos delta, and dy, this vertical component, if this is the triangle, okay, so this vertical component will be dv sin delta, right? Okay, now substitute the value delta in the above equation we get. So now we are going to substitute this value delta in the above equation. That means this is one equation and this is one another equation we found. Okay, so here delta already we found how much? Delta we found pi by 2 b square. Now this value I am going to put there. So here if I am going to put instead of delta pi b square by 2, then dx will be equal to how much? Dx will be dv cos pi b square by 2, and dy will be dv. dv is there sine, instead of delta we are going to put how much? Pi b square by 2, right? So here we found dx is this much, dy is your this much. So to find x and y, suppose we are going to consider a large distance. Suppose this point will be here, and we are trying to find out this distance. This distance, that means its x coordinate will be there and its y coordinate will be there. So to find point P, location of the point P, x will be how much? Integration of this dx, and y component will be integration of this value. Okay, so x will be equal to integration of dx. So here dx is this much, that is your cos pi v square by 2 into dv, and integration of dy, y will be equal to uh, sin pi v square by 2 dv, sin pi v square by 2 into dv. So equation number 1 and equation number 2, and here you can see that here as we consider a particular distance v, suppose from here to here particular point p is there and the distance is v, then we have to put the limit 0 to v, 0 to v. Then we can found x component and y component of a particular point on the spiral. So to find or to locate any point, on the coronal spiral or Euler spiral, we need Fresnel's integral, and the Fresnel integral is this one and this one. If 1 mark or 2 mark question will be asked in your question, you have to draw this figure and you have to write this one. To locate any point on the coronal spiral, we need the two integrals. Locate means to finding the x coordinate and y coordinate of this point. In first quadrant, we need two integrals, that is your called as Fresnel's integral. For x coordinate, this will be your 0 to v cos pi b square by 2 dv, and for y 0 to v integration sin pi b square by 2 dv. So this is these two equations, equation number 1 and equation number 2 are called as your Fresnel's integral. Fresnel's are called as your Fresnel's integral. Okay. Okay. So thank you so much for watching this video. Thank you.